opportunity to welcome you back. Good to have you back in the building. And then also, Williamsville is under a boil order. That's why you see our water fountains are covered. But County Market donated a bunch of bottles of water, and so you can help yourself between classes. And the bottles of water are located near the stairwell near the front entrance. Thank you.
There you go. Oh, there she is. Thank you. Okay. So, getting the rust off the gears here. What we're doing this week. Today, we are going to start or do our discussion over section 4. Now, I decided to postpone that vector lab just because with kind of how things ended up lining up as we look forward into the remaining part of the semester, it just kind of worked out the best to postpone that. So it's a bummer, especially since after I made that decision, we get nice weather. But that's just gonna have to be it, the way it is right now. So we're gonna do, like I said, the section 4 of chapter 3 discussion as part of chapter 4, because what section 4 deals with is relative motion. And so when you hear the term relative motion, or just even the word relative, what does that mean to you? Exactly. Each person has their own idea. Okay? You heard the phrase, it's all relative. What does that mean? Okay? It's okay. Yeah.
It's in relation to something else.
Exactly. It's in relation to something else, or each person might have their own take on it. Okay? You hear that, glass half empty or half full, that's all relative in how you perceive it. Okay? You got to have your own take on it. And that's kind of what we're doing today. And really, how I go about teaching this section of information is be thinking. Obviously, we want to be thinking, but be creative, okay? This is going to be where you can really determine the setup of these scenarios, which then lends its hand into what we're going to be doing in chapter 4, okay? Chapter 4, we're going to be dealing with Newton, okay? He was a thinker. But a lot of his stuff, is going to be dealing with, frame of reference, how we interpret, okay? How we envision scenarios occurring. So this is going to kind of give you a warm-up into what we're going to be doing in section 4. That's why today's homework is going to be relatively short, okay? I'll address my concern with some of the information in today's discussion when we get there. But we'll do that discussion today, and then tomorrow's already Thursday. I thought yesterday was Sunday, so I'm really with it this week. Tomorrow we're going to get into chapter 4. I'll give you your new materials. If you spoke with me before class period, make sure you stop by and I'll give you the materials before you leave. So tomorrow we'll get into section 4, or chapter 4, and in the first section, you get to draw pictures. And they're going to be fun. You can make them as simple or as elaborate as you so please. Kind of get your creative or artistic juices, if you have them, flowing. I mean, you've seen bits and pieces of mine. You might even see a little bit more today about how just wonderfully artistic I am. And so we'll be covering the next few days, a few sections of chapter 4, and then we will get into next Tuesday. That's right. I'm trying to do math here. Yeah, next Tuesday we'll do a quiz over what we are talking about this week. Okay. So be on the lookout. Again, things haven't changed a whole lot in terms of where we get our materials. There's quizzes, there's any homework. Just keep on top of Google Classroom. Okay. So that's what we're doing this week. How's everybody been? Bored? Great? Just living, huh?
Yeah.
Well, that's good. That's good. I'm sad no one came and saw me. I was bored here. No, I'm just kidding. We were working our tails off here while everyone's gone. So we kept pretty busy. But it's unfortunate that I didn't have an opportunity to do a Halloween video for you because I didn't. Did anybody you watch it? Oh, why not? What's that? Oh, so okay, yeah. I made a little spooky Halloween one just for a short while for honors camp. So creative juices, people. But I don't know if it's sad or funny. Okay, my wife decided to post it on her Facebook. Okay, I had probably 10 times the number of viewers because she did that. The sad thing, it wasn't students. It wasn't students because I looked at the numbers before it was released to or posted for those classes on Friday. I think over the weekend, only 15 maybe new numbers were posted after students were given the link. I've got 40 plus students in that class. So, I don't want to look too far in the future, but I'm pretty sure that I might become an influencer. I don't know. I've really thought about it. A whopping 230 views on a video. Come on. That's like right up there, right? All right. It's just a shame I didn't do TikTok. No, it's not. I don't do TikTok. Anyway. All right. Are we ready? We should all still have our notes, at least this section, in our handy dandy little binders. Okay? I'm going to turn the lights off. I need you to get your calculators out. Gotta move some stuff. All right. Getting some stuff together. Also, if by chance I'm giving my discussion today and I let out a little yelp or squeal, that's because my back is in pretty decent pain. You know how it happened? I don't know. I need someone to tell me because all it did was I was sitting in my chair on Monday here at school and I could almost barely get up out of that after lunch. So I don't know. And it's been in pain ever since. So y'all are what? 17-ish years old? Yeah. The next 20 years, ladies and gentlemen, this is the face you get to think of whenever you're getting every day older. Okay? Things just hurt, and you don't know why. Enough ranting about being old. Okay? Let's talk about relative motion. So today what we're going to do is we're going to describe situations in terms of frame of reference. Now, we have heard that before. Okay, frame of reference. Who would like to give us a refresher on what frame of reference is? Yes, in the back corner by the windows there. Yes. Saw your hand up.
Me?
Yeah.
I don't know.
Oh, yes, you do. What's frame of reference?
What you see?
Ta-da! Yes. What you see or how you see events happen. Okay? So it's all about what is visualized, what is experienced, what is witnessed. Okay? That's why, a lot of times they can say witness testimonies are so kind of hard to be reliable because everybody has a different viewpoint, a different vantage point, a different memory, different interpretation. Okay? But a lot of times those different interpretations aren't necessarily wrong. Okay? It just gives conflicting vantage points. Then we're going to solve problems involving relative velocity. Now, excuse me, we're going to incorporate a couple different things when we talk about relative velocity. Okay? We're not straying too far away from what we did in section 2 where we did the Pythagorean theorem and the inverse tangent and everything like that. Okay? So, nothing too crazy. But we're also going to be incorporating kind of a new setup. It's not necessarily a formula. However, if you want to write it down as a formula, you can. But it's more of a setup. And I'll be honest, I don't necessarily like the practice question, or not the practice question, the example that our notes give us. You're going to see more questions similar to what we're going to do as our practice questions together before your homework. Okay. But again, what I understand why the question is the way it is, because when things happen, there are a lot of things going on. Okay, so we'll be dealing with things that we've seen before, but in today's discussion, it's a matter of how you set it up or how you interpret it. Okay, so let's talk about frames of reference and the example that I was talking about. Okay, if you are moving at 80 kilometers per hour north, and a car passes you going 90 kilometer per hour north, if you are in that slower car going 80, and you see that 90 kilometer an hour car go past you, it doesn't appear to be that it's going that much faster than you, right? We've all been in those situations, whether you've been the passer or the passee. Okay, if you've been the passee, you see a car go by, and you're like, "Well, it's not going that fast." Okay, but that's all relative to you. But let's say for some reason, someone's standing on the side of the interstate. Actually, saw somebody walking down yesterday, like trying to hitchhike. So it still happens. They have a different frame of reference. They see that faster car going 90 miles an hour. Because that person's standing on there going, ooh, that's fast. Okay? So their frame of reference is different from the frame of reference of the individuals in the slow-moving car. And they're different from the individuals going in the faster-moving car. Okay? So that's where we get the idea of things are completely different depending on how you see them. And so we're going to be using the idea of frame of reference to help calculate some scenarios. Okay? Now again, I don't put a huge emphasis on this because, as I mentioned, some of it is review what we did in the earlier part of the chapter. And the other part is we're getting our outside of the box thinking going on here. Okay? You don't have to go too far outside of the box. Okay? But it just involves, it's less direct than what we might be used to. Another example of frame of reference. And if you get into a certain line of work and your job is to throw dummies out of a plane, okay? Well, it's a stunt dummy, so, maybe you're in movies or whatever. But think about two different vantage points that are going on here. If you are in that plane and you drop the dummy out so that it lands eventually on Earth, this top half of this picture is going to be what you see. It's going to appear, as long as you maintain your constant velocity, it's going to appear as though that dummy drops straight down because it's going to be right exactly where you dropped it in your frame of reference. However, most people aren't going to be in that plane. They're going to be on the ground. And so as that plane and dummy pass, we're going to see more of a parabolic frame of reference. Okay, we're going to see that dummy have a horizontal aspect in its motion. So again, see, depending on where we were, we could do a couple different mathematical setups. So when we are solving relative velocity, we are going to write down the individual velocities with subscripts. And those subscripts are going to be in a way to where they kind of flow with each other. And I'm going to see if I can't skip ahead before I go back. Okay? The very bottom of the following slide. So on this one, this bottom little equation or form is kind of what we go with. Okay? I want you to see if you can pick something out. Okay? General form is V with subscripts of AC. This would be the velocity that we're trying to figure out. Okay? Is equal to V with subscripts of AB plus V subscripts of BC. You notice anything about what's in that general form? Similar denotation to a triangle. Okay? That's one part of it. Look at the subscripts. Notice anything about subscripts? You're going to begin? Okay. So let's look at the unknown. AC. Okay? Then we hop over here on the right side of the equation. On our first velocity, what does that start with? A. Very good. What did our unknown start with? A. Okay. Look at our second velocity here. What does it end with? C. What's our second letter in the unknown? C. Do you kind of see where we're going here? Okay. Well, let's talk about it. So, this, on the previous slide, okay, I went back one again. This very last bullet point down here. You write an equation in terms of other velocities. Okay? So in our example of the fast and slow car, our unknown, we apply the letters FS, the subscript FS. Now, again, you can make those whatever you want to. FS stands for the fast car with respect for the slow car. So F for fast with respect to the slow car. And I did the wrong one. I don't know my letters. S. Okay? Fast car with respect to slow car. F for fast, S for slow. That's what you're trying to find out. Again, I've said it at least twice now. Say it again. I don't like this problem. Okay? But I go through it every year because I want to pinpoint everything and every thought process out there. But I promise you, it's not going to be that difficult when we actually do these. Okay? So that's our unknown. Let's look at the other two known velocities. Okay? One of them is the 80 kilometers. So that's the slow car. So again, slow car, S, with respect to Earth. because while you're traveling on the road, you're traveling on Earth. So you're going 80 kilometers per hour north relative to the Earth. Okay? What about the faster car? Okay? So that's 90 kilometers per hour north. And that's going to be subscriptive FE. Fast car with respect to Earth. All right. So what we're trying to figure out is, in terms of frame of reference, how much faster would we say that the faster car is going than the slower car? Just off the top of your head. 10 kilometers an hour. You didn't really have to go into a whole bunch of detail with that, did you? Okay. So what I'm getting ready to show you is how the book justifies what your answer is. And you are correct. You are correct. So I told you, it's not going to be as difficult as you did a pretty quick thing in your head, not having to do anything written down, right? Okay. But I want to show you how we set this up. So, you look at how we set up that form for the equation. When you write it in terms of V with the subscripts F of S, the subscripts start with F and end with S. So the other subscripts, meaning the two that we know, start with the letter that ended the preceding velocity. So if you look, we have FE plus ES. This one, the second one, started with the preceding velocity. And if we look here, we start with F and with S, just like we did with our unknown. Again, I can't say it again or enough that it's not going to be this crazy. Okay? Now, to throw a wrench in your thought processes here, the book decided to give you another vantage point. Okay? So you're an observer in the slow car. I drew a smiley face. You perceive Earth as moving south at a velocity of 80 kilometers per hour. Oh my goodness. Stop and think about that, folks. How many people have to be involved? Well, to me, there's too many involved here. And so, when you compare the frame of reference from the person in the slow car to that of the person on the side of the road, okay, you get all kind of wonky. Okay? I hate going through this problem. I do. Okay? But I find it necessary to talk about it. Because after everything's said and done, you end up with an answer you did in your head. Okay? So, in order to not sit there and ball ourselves up, let's do a couple problems to show you that it's not going to be too crazy. Okay? So, we have a moving walkway at an airport. Okay? Now, has anybody been to an airport where or anywhere they've had these moving walkways? Okay. Tell me you don't sit there and try to walk as fast as you can when you get on those things. But then you have to really slow up at the very end because otherwise you're going to go, whoop! Okay? So, we're going to have this moving walkway. That moving walkway has a velocity of 1.50 meters per second to the west. Okay? I'm going to sit here because I'm going to do the work on here. A man rushing to catch his flight runs down the walkway with a velocity of 4.20 meters per second to the west, relative to the walkway. If the walkway is 8.50 times 10 to the second meters long, how much time does the man save by running on the walkway as opposed to running in a non-moving surface? So how fast does that moving walkway actually help, or how much time does it save him by using that moving walkway as compared to just running on the ground? Okay. If we don't get through all these problems today, we'll talk more about them and then we'll go from there with the homework. Okay. I spent too much time on that stinking equation for a problem. Okay. Let's do some practice here. Actually, I'm going to take this light off so that way you can see a little better. And now this one's black. Okay, in the back, can you see that? Okay. All right, so what do we know? We know that the velocity of the walkway, so just the walkways itself, with respect to Earth. So basically, how fast is that walkway going? Yes. 1.5 meters per second. In what direction is it going? West. In what direction is the man running? West. In typical vector form, what sign would we use for something moving west? Negative, right? But since both objects are moving in the same direction, we don't got to worry about that. Okay? So now comes the fun part. Giving this a subscript. So I'm just going to say this is the walkway with respect to Earth. So VW. So subscripts of WE. Walkway with respect to Earth. See where I got those? Okay, so then we write down the velocity of the gentleman. Okay. So what was the gentleman's velocity? Okay. And so that man, it said, was relative to the what? Walkway. So M, man, relative to walkway, W. One other bit of information we need to know is the length. It's 8.50 times 10 to the second meters. So we need to set up a form, okay, of an equation that we can use to help solve for this. Okay, well, first of all, our unknown, it's going to be a velocity. Okay. So what is the velocity of the unknown? What do you want to call that? Using knowing the subscripts, woo, Rust. Knowing the subscripts that we have used here, what do you think we should call this? What's that? Very good. ME. Because we're trying to figure out the man's velocity with respect to Earth. Okay? And so now, again, you don't necessarily have to do this if you don't want to. But to set this up, you'd have VMW plus VWE. Again, you notice, start with M, end with E. And the W on the first velocity was carried in to be the first letter of the second velocity. Okay? Again, I'm going to tell you, I don't care how you set it up. I'm just showing you how what we discussed today would translate into this problem. All right, so then we simply just plug in your numbers and add them up. So we see that the man is traveling 5.0 5.70, meters per second west. Okay? Now, does that answer our question? No. What are we actually trying to find?
Time saved.
Time saved. So, what bits of information can we use to help us calculate the time it would be if he used the walkway or didn't use the walkway? What information do we know? We know his velocities, okay? And we also know the distance. So, we can take the formula for velocity, which is distance over time, and rearrange it to solve for time, where we get distance over velocity. And so with our walkway, okay, we're going to do this a couple different calculations. Okay, let's calculate how much time was saved with the walkway, or what his overall time was. Okay. So again, the distance was 8.50 times 10 to the second meters, divided by his speed with the walkway was what we calculated up here. 5.70 meters per second. So how long did it take him to travel this length on the walkway? Keep it in seconds. Very good. So now let's do without walkway. Same thing. 8.50 times 10 to the second meters. His speed that he was actually traveling without the walkway. Can anybody figure out what that value is? Exactly. 4.2 meters per second. Very good. 202 seconds. So we've now calculated the amount of time it takes for him to do both, right? So we have to find how much time was actually saved. So we just take the difference. 202 seconds minus 149 seconds. How much time did he save by using the walkway? 53 seconds. So, again, if you didn't get hung up on trying to set up your general form, all it comes down to is addition and division. Now, I didn't get to where I wanted to today, so hold off on the homework, okay? We'll talk more about this tomorrow. Again, since I didn't get where we are today, just be on the lookout in case I end up moving something by the end of this week. Okay, I might have to bump something. Not 100% certain yet. So I'm going to stop the video there.